Welcome back to the channel. Today we're going to make some changes to our small engine test stand. This test stand has seen better days and we're going to be scrapping it real soon. But before we do that, we need to run some experiments, and the data that we gather today will help us build a new test stand. So this test stand uses an alternator to put a load on whatever engine we're testing. The power generated by the engine spinning the alternator is dumped into this resistor load bank, and basically the resistors dissipate the energy as heat. This setup has served us well for 5 or 6 years. However, time has taken its toll, and the vibrations from running engines on this test stand have damaged all but one of the very expensive high wattage ceramic resistors. Now, this test stand is for general purpose testing, and it's not a calibrated piece of equipment. Eventually, we want to put together a precision test stand that can measure horsepower so we can validate various engine modifications and to do stupid engine experiments, which I love to do. Now, what we really need is a dyno. Of course, we did build a prony brake dyno years ago, and this guy has the capacity to electronically measure the torque and the RPM, which can then be mathematically converted into horsepower. This prony brake dyno has its limits, and it was designed to work only with the small block 212cc Predator engine. The big block 420 or any other engine will not work on this dyno. Now, another limitation of this little dyno is it has an operational runtime of about 30 seconds before it overheats the friction material used for the brake. It's a brake dyno after all, and brakes do get hot quickly. Anyway, we want to have something that'll run a variable load over a longer period of time. I figure a runtime of about 30 to 45 minutes at full load would suit us a lot better. Now, when it comes to working on and building dynos, I have a fair bit of experience. This monster is something I built in my garage way before I started my YouTube channel. This guy has a hydraulic power absorption unit, and it was a lot of fun for experiments. This is a big dyno, and it was used for small automotive engines. Now, the hydraulic power absorbers like this one and the friction absorbers like this one are kind of two ends of the spectrum. They work, but I think an electrical base absorber is the way to go, at least for me. So today we're going to focus on an unusual and extremely cheap way to absorb power. So keep in mind, there are many different ways to absorb power, but I want to do it as cheaply as possible. The data that we gather from today's experiments will be used to build our future low-cost dyno test stand. Anyway, we're going to replace this resistor load bank with a garbage can. Well, sort of. You see, we're going to modify the garbage can slightly and install these two 4,500 watt hot water heater elements through the side of the trash can, and then we can fill the can with water. That way we can dump a metric ton of power into the heater elements, and the water will keep everything nice and cool. Well, that was the original plan, but I screwed up. It turns out that these elements are not 4,500 watts each. Nope, it turns out both of them combined are 4,500 watts. That kind of puts a wrinkle in the plan, but no worries. I have the correct elements on the way, and these lesser elements will be enough to validate today's experiment. Now, the garbage can is obviously not ideal, and we're just using it to prototype the system. We will eventually replace it with a custom container made from a 55-gallon steel drum. However, today this will work just fine. Anyway, for the alternator, we're going to be using this guy. It's a 140 amp PWM alternator from a Jeep Liberty. Now, 140 amps really isn't a lot of power, and we'll upgrade to a 250 amp alternator eventually. But those are expensive, and we have this unit in stock, so today we're going to use it and abuse it. This alternator was modified, and it doesn't have a voltage regulator. So what that means is we can apply voltage directly to the brushes and overdrive the fields in the rotor, and that's going to allow us to generate insanely high voltages. And before anybody gets scared, we've done this before in the past on the petroleum battery experiments, and we haven't destroyed an alternator yet. As a matter of fact, we have a set of heavy-duty diodes in stock just in case we do blow the rectifiers. But so far, these alternators have proven to be indestructible. Actually, I look forward to blowing one of these up, but that day hasn't come yet. So no worries, if it blows, and that's data that we can use, but chances are this alternator will survive yet another day. The voltage that will send directly to the brushes on the alternator will come from a little PWM power supply like this one. This guy will allow us to apply variable voltage to the brushes. Now, we need something like this because it takes about 5 to 10 amps to overdrive the rotor fields, and that's not something you can do with a rheostat or potentiometer. So the alternator modifications and how to connect the PWM power supply to the alternator was covered in quite a few petroleum battery episodes. However, Season 4, Episode 41 contains a lot of detail on the alternator modifications and wiring if anybody's interested in more information. Anyway, this knob is our new way to adjust the load on the test engine. On our older control box, we had a switch to turn on each load. Well, no more. Now we can just twist the knob to increase and decrease the load. Very nice. Anyway, let's get started with the trash can modifications. Alright, this is what we're going to build. First of all, we're going to have to drill 2 holes in the trash can so we can insert the hot water heater elements. Hopefully that makes sense. Now the output of the alternator will wire directly to the heater elements. As you can see, there's no battery on the output side of the alternator, and that's because the voltage coming out of the alternator can vary between 0 and 80 or more volts. We've seen over 100 volts from these things, but today I'm not sure what to expect with the load we have on the output of the alternator. Anyway, this PWM power supply gets wired directly to the brushes of the alternator, and turning this knob clockwise will command the alternator to start producing volts. Remember, this alternator doesn't have a voltage regulator, and we can command it to produce whatever voltage we want. This gizmo is diffused, just in case things go south. Now, using an automotive alternator is the cheapest solution. These guys are robust, and they were designed to produce a lot of current. So, internally, the windings are of a lot thicker gauge wire. Now it's a bit sketchy how much voltage these can handle, but generally the enamel insulation on the fields are good for a few hundred volts. The diodes, on the other hand, well, the jury's still out on that one. As soon as I blow one up, you folks will be the first to know. Right now, our plan is to ride the wave of good luck and send it and see what happens. Best plan ever. Now, if you're familiar with the petroleum battery electric golf carts we built last year, this is basically the same concept. If you replace the heaters with an electric motor, something magical happens, and you can get an electric golf cart back on the road without using heavy and expensive batteries. Works like a charm. So these cheapo trash cans leak water, so I went ahead and applied Flex Seal to all the seams, and it actually worked. So that was an easy solution. These heater elements are fairly long, however they will fit lengthwise inside the trash can no problem. The ones that I'm using today are not the right ones, and the correct ones are basically the same size, so that's good, and we can use these to verify the system works. Anyway, these elements run between $13 and $15, which is super cheap, and that's why we're going this route. So for a leak-free penetration through the trash can, we're using these 1-inch bulkhead thingies. These guys run $13 each, and they're definitely within our budget for sure. Off camera, I went ahead and marked the location for the holes that we need to drill. I reckon we'll start off by drilling pilot holes with a dull drill bit. Next, we'll grab one of these El Cheapo step bits and enlarge the hole. And now we can make the hole a little bit larger. So these doohickeys still don't fit, and I don't have a bigger step drill. So no worries, we can finish the holes off with this mini belt sander. I've already done this one, and this thing works great. Okay, these bulkhead thingies now fit. It's interesting. These things have left-handed threads on them for some reason. Fast forward a few minutes and I have the trash can filled with water to leak test it. So far, so good. The Flex Seal and the rubber grommets on the bulkhead thingies are holding back the water no problem. I'm going to let this sit for an hour just to make sure. 1 hour later and we're still leak free, so this is going to work out pretty good as far as leaks go. Off camera, I went ahead and switched out the Cadillac alternator with this modified Jeep Liberty alternator. Basically, it was a straightforward mechanical swap. I also wired in the old shunt so we can measure the current coming out of the alternator. All the load resistors have been removed, however I did retain the bus bars. This side is negative and this side is positive. Keeping these bus bars is just a shortcut for now. We'll get rid of them and eventually we'll use insulated terminal blocks, but these will work for today. Fast forward a few hours and we have the trash can wired. The heater elements are wired in parallel, and unfortunately we only have 6.7 ohms of resistance. So for the non-electrical people, the higher the resistance, the less of a load we will have, and 6.7 ohms is not going to be enough of a load to stall the engine. Like I mentioned earlier, we do have different heater elements on the way, and they'll provide a much bigger load, but for today these will work. The wiring is sized for a much bigger load, so we're golden as far as that goes. Anyway, this is how the trash can is connected to the test stand. Of course, the can will be on the floor and not up on a pedestal. So this is the new control box, and it's real simple. We have an on-off switch and a load adjustment knob. I went ahead and used drawer pull handles to guard the controls in the event this control box falls on the floor like it usually does. On the inside, the wiring is straightforward and it's just in and out plus a switch. This PWM power supply has the option to remote mount the potentiometer, so that's pretty much what I did. The wiring is 14 gauge and that should be plenty for the amount of power this guy will consume. At this point, I think we're good to go, so let's see what happens. Okay, we're all set to test this thing for the first time. The trash can is filled with about 17 gallons of water, which should be plenty. It'll be interesting to see how hot we can get this water. Right now I'm showing 50 degrees Fahrenheit and the ambient temperature today is in the mid 50s, which is nice for February. So what we're looking for today is how much voltage we can get from the alternator and of course how many amps the hot water heater elements can absorb. I have a feeling we're going to be running a bit on the light side because we have the wrong elements installed. Now I'm also interested in how hot the alternator gets, and I'm not afraid of letting it smoke if it has to. So far we've had great luck with these alternators, and this one's already seen a lot of abuse when it was installed in the Desperado for the petroleum battery experiments. Now, from the petroleum battery experiments that we did last year, we learned the absolute most power that one of these Predator engines could develop before it stalled was about 3,000 watts of electricity. Of course, that number may seem low to some people, but you also have to factor in that alternator is only 60% efficient. So the math to convert horsepower to watts is a bit funny. No, not that kind of funny. Well, let's see how much energy we can dump into the trash can. So the control box is off and the dial is set to 0. Today, we're going to leave the box on the floor so it can't fall like it usually does. In case you didn't watch last week's video, this engine's equipped with a slightly larger and fully adjustable carburetor, and we also were able to retain the governor. So we're showing about a half amp on the gauge with nothing activated. Interesting. I think the vibrations are coming from the crankshaft pulley being out of balance, and I need to check that eventually. Well, let's give the alternator some juice and see what happens. The main power's on, and so far so good. Now let's overdrive the field voltages. I can hear the engine loading down, so something's working. Well, we've maxed it out and the engine has installed. Interesting. Let me put this guy back on the floor and we'll check a few things. The alternator is putting out about 12 amps, which is kinda low, but then again we're using the wrong hot water heater elements, so that makes sense. The voltage gauge won't work on this setup, so we'll have to read the voltage with the meter. Okay, this is interesting. At the garbage can we're measuring 82 volts DC across the heater elements, so we're making power. Now if I do some quick math and multiply the amps by the voltage, we're getting about 984 watts. If I do the Ohm's law math, that works out to a load of about 7 ohms, which is kinda what we measured with the ohm meter. Well, now I know that the hot water heater elements are consistent and the resistance doesn't change when they get hot. Let's run the engine up to max speed. Well, that's cool, we're getting a lot more power out of the alternator. I don't have a tachometer hooked up today, but this should be about 3600 RPM. Let's check the voltage now. Wow, 126 volts DC. That's pretty cool. So once again, if we do the math, now we're at 2300 watts. Yep, that checks out. That's about what we should get with a 7 ohm load. Unfortunately, we need about 3000 watts to stall this engine. It's amazing that we're getting 126 volts from a 12 volt alternator. I'll bet the rectifier diodes are not happy with a 950% increase in voltage. I'm not sure how much they can actually take, but this is very interesting and amusing to me. So 950% overvoltage is epic in itself. But we're also pulling 18 amps through the diodes. Kids, don't do this at home. Fast forward 45 minutes and the poor little alternator is still going strong. The test stand has been chooching away and dumping 2300 watts of energy into the garbage can, no problem. The water does feel a little warmer, which makes complete sense. So it would seem we need at least 15 gallons of water, but we may get away with a little bit less. Well, to answer a question that nobody asked, you can pump 125 volts DC at 18 amps out of a 12 volt alternator and the diodes won't explode. It's interesting, however, I don't recommend doing this. Alright, well let's shut this contraption off. Well, the alternator is hot, but not too hot. I suspect this is about normal hot, if that makes any sense. There was no weird smells, and I have no problem touching the case of the alternator, so I'm going to call this a win. The trash can full of water is measuring in at 72 degrees Fahrenheit, so we started at 50 degrees and we were able to raise the temperature by 22 degrees over 45 minutes. Basically, we were running the system at half power. Now, when we replace the hot water heater elements with the correct ones, that'll obviously put a bigger load on the alternator, and we should see a drop in voltage. I'm thinking at full power we should see around 60 volts, which should be fine. You see, from the petroleum battery experiments, we had no issues running the alternator at 60 volts at a full load for a few hours. Today's experiment was basically a data collecting experiment. Normally, I wouldn't publish something like this on YouTube, and this is the kind of stuff I do off camera to develop methods and procedures. But the information that I use for my projects has to come from somewhere, and today you saw what I do in order to confidently build wacky projects for YouTube. Most of what I did is not necessarily stuff you would find in a textbook. As a matter of fact, I violated a lot of common sense rules because, well, this was an experiment for the purpose of validating an idea. So the goal was to build a load bank that could absorb a lot of power for an extended amount of time and do it on the cheap. So with the information I gathered today, here's my plan. We buy a 55-gallon drum off Marketplace for about 20 bucks. These things are cheap for what they are. Although it does have to be the kind of drum that has a removable lid. That's important. Anyway, then we cut it down and re-weld the drum so it holds about 15 gallons of water. Next, we'll drill out the drum to accept between 4 and 6 heater elements. We'll probably start with 4, but we'll leave room for 6. Then we'll wire the heater elements in parallel for the best possible load. So far, so good. The drum with the 4 heater elements and the 4 bulkhead fittings is going to cost us about $132, which is okay. Now we need to make this thing portable, so we have to get a drum dolly. A cheapo drum dolly is going to run us 35 bucks on the jungle site, so now we're at $167. Stuff adds up, but keep in mind this load bank had $900 worth of busted resistors in it, so we're saving a bunch of cash going this route. Now, we'll probably add a few doodads here and there, like a drain system that we can use to flush the hot water out if we're going to do a longer than expected load test. All in all, it's a solid plan, and if we blow a heater element, well, the new ones are only 15 bucks, so this system will be cheap to maintain. Today was pretty much a behind the scenes look at what I do off camera. A lot of what you see on camera for our videos takes a bunch of research and testing in order to make the magic happen for YouTube. I hope you got some kind of enjoyment out of this video, and perhaps this inspired you for a project you may be working on. We'll see you next time. Until then.